All right, welcome to Chapter 1. And in Chapter 1, we are going to be spending a lot of time working with graphing functions um, and talking about how can we sketch out different graphs and look at different types of issues that are happening within them. And big part of this is being able to identify the different characteristics that happen within functions. So we're going to take a look at what makes a function continuous, whether it's increasing or decreasing. If it's bounded, we're going to talk about local and absolute maximum and minimums, talking about some asymptotes, and then also talking about the end behavior and an introduction to limits, which you spend a lot of time going over once you get into calculus. So starting out with continuity, determining if a function is continuous or not. So up here I have four different graphs and I have four different examples. The first one here is what we would say is a continuous graph because if I were to take my pencil and draw over this graph, at no point do I have to lift up my pencil at all. It is a continuous graph from left to right. There are no breaks into it. The next one here is removable discontinuity, and what's happening here is as I'm tracing, I stop, I would have to pick up my pencil, and then I'd have to continue through, and this open circle is referring to a hole that is in our graph, and I'll go over an example of having a hole here in a moment. Then there's jump discontinuity, which if you remember having your step functions, that's a good example of it. But here you definitely have to pick up your pencil, and rather than just moving it over a quick millimeter here, we're moving down, or we're moving up. There's a big step that's taken place. And then we have infinite discontinuity, which you are looking at separate branches here, and we are going to include having some asymptotes. And going over, what an asymptote is where I want to go next. So if you remember, an asymptote is an invisible vertical or horizontal line that a graph approaches but never touches. Now, the one thing you have to be careful of is that horizontal asymptotes, those can actually be crossed. Vertical asymptotes will never be crossed. And so just being very careful about that. We'll spend way more time on this once we get into our rational function unit, however. So here I have an example of a function that has some vertical and horizontal asymptotes. If you heard that noise, that was my child's garbage truck that was underneath my kitchen table. Anyway, so it's got vertical and horizontal asymptotes that are on here. And at this point, I'm not going to have you guys necessarily identify how you get these, but for sure being able to look at a graph and be able to see them that way. But perhaps some of you are going to be able to look at the function here and be able to identify where those vertical asymptotes happen, because vertical asymptotes are when a function's undefined. Well, rational functions or fractions, functions that are dealing with fractions, we can never divide by 0. And so if you look at your denominator here where you have 4 minus x squared, thinking about, well, what would x have to be in order for us to get 0 down here in the bottom? And our two possibilities here would be -2 and +2. So at those two scenarios there, your graph would not exist. Therefore, you've got your vertical asymptote. As far as that horizontal asymptote goes, that's going to be something that we look at a later date. But just being able to look at this graph here and kind of be able to see that these graphs here are going to this value of -2, which we'll be taking a look at later. Here's another example of some asymptotes and looking at those. Here I have two vertical asymptotes. Once again, working with a rational function, x squared minus x minus 2. So if I factored this out into x minus 2 and x plus 1, I could see that, well, +2 would not work for a value of x, and -1 also would not work. And so those two would be our undefined values. So we'd have vertical asymptotes there. This graph also does have a horizontal asymptote along your x-axis. And so we'll be talking about how that is telling us what our end behavior looks like. Just a little, like I said before, you are able to pass over horizontal asymptotes. So you'll notice that in the middle of this function, we pass over your x-axis. An example of removable discontinuity is one right here. If you look at this, you probably think that this is a continuous graph because you see a nice straight line. But be aware that this looks like a straight line, but its function is not in the form of a straight line. Y equals mx plus b, and then here I'm working with, once again, a rational function. If I look at this rational function here and I look at the denominator, I see x minus 2. Well, since we can't divide by 0, that means that x cannot equal positive 2. So at positive 2, there's actually a hole that's sitting in our graph. And you're not going to be able to see this unless if I had my graphing calculator up here and I had the calculator trace along this line, all of a sudden when it got to positive 2, it would show an error, and then all of a sudden it would reconvene. So this is what we call removable discontinuity. Why is this? Why does that graph resemble a straight line? Well, x squared minus 4, if you were to factor that out, that would be x plus 2 and x minus 2. And here you end up with factors of x minus 2 in your numerator and denominator. And so what your function is resembling here is x plus 2. So we have a slope of 1, a y-intercept of 2, and that's why it's graphed out as a straight line. Again, we'll spend a lot more time with this stuff once we get into our rational functions. All right, talking about increasing and decreasing parts of a function. Increasing, something's going up. Decreasing, something's going down. A function is increasing on an interval if for any 2 points of the interval, the slope between those 2 points is positive. So you'll notice that over here on my graph here, I have 2 points and it's going uphill. We are increasing from point A to point B. If we were to look at that slope right there, it's a positive slope. So talking about where is our graph here increasing, it's increasing at the interval from -4 all the way over to +2. If you wanted to, you could use your interval notation. If you don't want to use your inequalities, that's fine too. Function is decreasing on an interval if for any 2 points in the interval, the slope between those 2 points is negative. So notice here that I'm going downhill. Between these 2 points, my slope is negative. So it looks like I'm going for my value of x is decreasing, where x is greater than or equal to -6 and less than or equal to +9. So we're looking at the interval from -6 to +9. Lastly, you have a function as constant on an interval if any 2 points in the interval, the slope between the 2 points is 0. So if you have a flat line, then you're talking about the fact that your function is remaining constant. So here I have a straight line, and so my function is remaining constant from -5 to, it looks like, +6. So again, on the interval from -5 to +6, it's remaining constant. Then taking a look at if a graph is bounded or not. There's a couple different things that we can have here. We can have a function be bounded below. We can have a function being bounded above. It can be bounded both above and below, and it cannot be bounded at all. The big thing here is understanding, does your graph have a maximum or does it have a minimum? If it has a minimum, and we'll be talking about what I mean an absolute minimum, then that means that your function is bounded below. That means that nothing can go below that point right there. And so your minimum, the fact that you have a minimum right here, that's the lowest point, and so that means it's bounded below. Can't go any further. Bounded above, just the opposite here. You're going to be looking at having a maximum, and so that's going to be referring to your absolute maximum. If you have a maximum and a minimum, then that means that you are bounded both above and below. So it's going to be on both. One thing that I'll kind of note here is that you can have horizontal asymptotes, and horizontal asymptotes can act as minimums and maximums because it won't go possibly above or below that. So understand that those can also help us keep our functions bounded. Not bounded at all would be if you do not have a maximum, if you don't have a minimum. So you'll notice that on this function here that it's going to keep going up towards positive infinity for y, keep going down towards negative infinity for y, so there is no maximum, there is no minimum. Therefore, it's not bounded. So I used, with the idea behind being bounded, I used the fact of having maximums and minimums. Well, let's talk also about what is the difference between local and absolute maximums, and taking a look at those two. So local minimums, local maximums are any of the low points on a graph. I refer to those as the valleys of the graphs. And we can have local minimums, we can also have absolute minimums. An absolute minimum would be the lowest point that's possible here. So right here I have an absolute minimum. That's the lowest point that our graph goes. The thing is, here I have another minimum, but this would be referred to as a local minimum. So both of these are low points in our graph, but then here, because this is the lowest point, that's our absolute, and this one doesn't quite go down as far, that's your local. Now, this graph does not have a maximum because it's going up to the sky in both directions here, but this point right here is going to refer to that as a local maximum. And so although there's no absolute maximum, there is a local maximum. Just kind of changing this around here, notice that I have, on this next graph here, I have two high points. The highest point right here, this is going to be our absolute maximum. And this other high point that we have here, this would be referred to as our local maximum. I have one low point that's on here. This low point is going to refer to as a local minimum, because I don't have an absolute minimum, because my graph is going down in both directions. Here's an example of where you have no absolute minimum or maximum. I have a local minimum and a local maximum, but I have no maximum. I have no minimum. As you look at the graph here, we're starting out at negative infinity and going all the way up to positive infinity. And so here I'm working with a local maximum, and here I'm working with a local minimum. There is no absolute maximum or minimum. All right, so what I'm going to do now is just take a quick moment to kind of recap of everything that I've currently talked about, just by looking at a single function, and just try to look at some things that we've talked about so far this year, even as we look at this graph. So with this one here, answering the question of, is it continuous? Yes. There are no holes in it, there's no jumps or anything like that. As far as our domain goes for a function, yes, domain and range are going to come back to us. So we are looking at domain of all real numbers. We're also looking at a range of all real numbers. As far as what interval is this function increasing at, it is increasing for this first part. So here's an increasing part of this graph, here's another increasing, and then here we can see the function is decreasing. So as far as that interval is increasing, it's going from negative infinity to -5. And so we're saying that x would be less than or equal to -5. And actually, I mean, technically I could just be putting x is less than -5 at that maximum point right there. It's neither increasing nor decreasing. And then also we're going to be increasing at values of x that are greater than or equal to +2. As far as where is it decreasing from, we're going from when x is greater than or equal to -5 and less than or equal to +2. This graph is not bounded because there is no absolute maximum, there is no absolute minimum, which that gets into our next thing here as far as our extrema. There's no absolute maximum or minimum, but there is a local minimum, and we have a local minimum at 2, -1, -4, and then we have a local maximum, and we would have a local maximum at -5 and 1, 2, 3, +5. So just being able to look at a graph and be able to look at a few different things from that. Alright, so then lastly what I want to do is talk about end behavior and working with limits. Really what limits are is it's what's happening to your function as x gets really, really big and what happens as x gets really, really small. It's trying to get you to look beyond what you see on the graph and what's happening in the, again, in the end. That's why it's called the end behavior. Limits are very important once you get into calculus and you start looking at limits as they approach different sides of your function. Here we're just going to be looking at what is happening as x gets really, really big and what's happening as x gets really small. So I ask this question to you. As x goes to positive infinity, what happens to the y value? So as x is getting bigger and bigger and bigger, what's happening to your y values? And if we look at a quadratic here, if we look at the parabola, and we think of it as y is equal to x squared. So as x gets really, really big, well, what's going to happen to your y value when you square that number? It also is going to get very large. It's going to grow at a really fast rate. And so as x approaches positive infinity, y is also going to be approaching positive infinity. And so what we do here is we talk about what's called the limit. So this is referring to our function of f of x. So the limit, abbreviated as LIM, of your function of f of x as x approaches positive infinity is equal to positive infinity, and that's it. So we use the LIM to represent limit. Underneath that, I put x with a little arrow approaching infinity, and then naming the function f of x. We also want to take a look at, well, what's happening for your limit as x is approaching negative infinity. So now I say, well, what happens as x goes towards negative infinity? What happens when you get a really small number? If you take something like -1 million and you square it, well, we know that any positive number or any negative number squared is always going to give us a positive number. And that's why we have the U shape that we do have for our function. So as x goes towards negative infinity, your y value is still going to go to positive infinity. And so the limit as x approaches negative infinity, the function f of x equals positive infinity as well. Take a look at another example here. So looking at our function here, I'll just say this is g of x, and this is our cubing function, so x to the third. And as x gets really large in this case here, what's happening to y? Well, if I take any number to the third power, just like when you square it, it's going to grow very large very fast. So the limit of our function of g of x as x approaches infinity is going to once again be positive infinity. Now that's going to change for the negative side of things. So now if you look at as x approaches a really small number, as x gets really small, notice that our graph here is down here in the third quadrant. A negative number to a third power is always going to be negative. It's just going to be a very, very small negative number then. So if you think about taking -100 to the third power and think about how small that number is going to be. And so those values of y are going then down towards negative infinity. So the limit as x approaches negative infinity of our function g of x this time is going to be negative infinity. Here's a graph where we're going to be looking at an asymptote that's going to give us our end behavior. And that's where horizontal asymptotes come in to this. And you'll notice here that your graph kind of tapers off. So eventually kind of plateaus off and it's going to this value. And that's where our horizontal asymptote is, and that looks like it's going to be a positive 3. So as x gets really, really large, what's happening to our graph for y is it's approaching 3, but it's just never going to cross it. And so here our limit, we'll name this function, we'll call it k of x. So the limit of k of x as x approaches infinity here is, in this case here, it's going to equal positive 3, because that's where it's going to go to. On the other side of things, as x gets real small and as it goes towards negative infinity, notice that it also goes towards positive 3. And so the limit as x approaches negative infinity of k of x is also going to equal positive 3. So you can have functions go to infinity, plus or minus infinity, and you can also have them go to a particular value. One last one that I want to look at here is this graph and kind of trying to see what's happening here. There's kind of a little hill to this, and then all of a sudden it starts coming back down. Well, what's happening to this graph here as x approaches infinity is your y value is actually coming back down to 0. So it's starting at your origin here, it's going up, and then it's coming back down to 0. And so this would be the limit, and we'll name this function h of x. So the limit as x approaches infinity for the function h of x, this would be approaching 0. It's approaching your x-axis. It's doing the same thing down here below your x-axis. And so the limit as x approaches negative infinity for h of x is also going to equal 0. And we'll definitely talk about, again, those end behaviors later on. Alright, so I know that this video is getting to be a little bit long, but there's just a lot of information that's in here. What you're going to be asked to then do is try and draw some sketches out for yourselves, just kind of giving some of these different characteristics, and understand that there's many different ways that you could draw these, just trying to get a few of these important parts. So I just want to go through a quick example of kind of what I'm looking for on your end of this and what it should kind of, I guess, kind of look like. So here I have 6 different conditions that I want to try and graph out here in a function. So it says that f is decreasing on an interval from negative infinity to negative 3 and from 1 to 4. Notice that it's increasing from negative 3 to 1 and from 4 to 0. So these are intervals for x. So what I'm going to go ahead and just do real quick is I'm going to kind of break this up into those different areas. So from negative infinity to negative 3, we are going to be decreasing. From 1 to 4, so from 1 to positive 4, 1, 2, 3, 4, our graph is also going to be decreasing. It's going to be increasing from negative 3 to 1 and from 4 to infinity. So kind of just thinking about what's happening. So I'm just going to kind of draw a little line here to help me. So decreasing here, increasing here, decreasing again here, and then increasing at this point. So that's just kind of a little kind of scribble that I can use to kind of help me with my graph here. It says that f has a removable point of discontinuity at x equals 2. So somewhere on my graph here at x equals 2, there's going to be some sort of hole that's going to be taking place. So there's going to be a hole somewhere at x is equal to 2. F has a local maximum at 1, 7, so I can go ahead and plot that point. So I can go over 1 and up 7, 1, 2, 3, 4, 5, 6, 7. So I know that we have to have a local maximum at that point. Now that's not an absolute maximum, so I can be going in both the directions. It does have a minimum at negative 3, 2. So -3 and -2. So now that is a minimum, so my graph cannot go below that point right there. And then lastly, it tells me that f of 2 is equal to 0. So actually, I'm going to have a point right here. So where that hole is, that point is going to be jumping down. So now, if I just go ahead and kind of look at the points that I have and take a look at my slopes that I'm working with, I can try and have a general idea of what this graph looks like. In the first section here, I need to be decreasing, so I'm going to go to that first point from the left and decrease. And all of a sudden, it's going to increase. And what I'm going to do here is I'm going to go ahead and I'm going to get up to that second point. So it's increasing, and now I'm decreasing once again. So from, maybe I want to go right here to that hole, and then you know, I could continue on until I get to this point here, and then all of a sudden I can go back up, and there's an example of what this function could look like. All of those conditions that are listed right there would exist for what I have drawn out. You could definitely change a few things around to this, but in general, those things are all taking place. So once again, I know that there's a lot to this one, a lot more so vocabulary and kind of being able to identify characteristics that we'll then be using at a later date.